All right, so here we go. New topic today. Something a little different. We're going to look at it's kind of disconnected with the rest of Unit 3. This is sort of one that's just sort of by itself. Close all the Chromebooks all the way up, please. And we're looking at our notes here, piecewise functions. This is a different kind of a thing in math. You've probably never seen this before. Think about some situations where we use math in the real world. A lot of times we use math to model the way things work in the world. Like my background is in physics. In physics, that's what it's 100% about, is just trying to explain the way the world works using mathematical models. So what if, take this example, what if we took somebody in a helicopter up to a tremendously high altitude to go skydiving? Okay? When you jump out of the helicopter's just hovering there, really high altitude. What's going to happen? Tell me what that story is going to look like when you jump out of the helicopter. What happens first?
You get busted by the evidence from the bodies.
Okay, you do. True. Ignoring that though, what's going to happen to you when you're going to fall? What happens at first when you fall? Okay, but you're starting off with no speed, right? And you're accelerating. You're picking up speed for a while. Agreed? Okay, so that's one thing that happens initially. Do you accelerate forever? Okay, there's a point where you hit terminal velocity. Where the force of the air pushing up on you matches your weight and you fall at constant speed after a while, right? Terminal velocity. Okay, so then, so far there's at least two things going on that are different, right? You accelerate for a while, that's one thing, and then you hit terminal velocity, which is something different. You're moving at constant speed, you're not moving at speed. Okay, so then what happens when you pull a parachute? What happens there? Okay, good. So you slow down in a hurry, don't you? Right? There's going to be a real, like you're going to feel a tremendous jerk on the harness, and it's going to decelerate you very rapidly, right? A lot of force acting on it. You slow down, and then once you slow down, eventually you just kind of float to the ground at a much, much lower terminal velocity because of the parachute, right? Everybody agree? So when you agree, there's four completely different things that are going on in that situation, right? If we were to have a stopwatch that would start when you jump out of the plane, and we wanted to come up with some kind of a function that's going to predict what's my speed at which I'm falling, given, at any given time. So at time 0 is when we start our skydiving excursion, we jump out of the helicopter. At any amount of time, we ought to be able to make a prediction. We should be able to come up with a mathematical model that's going to make a prediction about what our motion is going to be like at any time after we jump out of the plane or the helicopter, right? Okay, but the problem is, there's four completely different things going on. We've got separate equations for the first part, when we're picking up speed in free fall. We've got a different equation that would make a prediction when we're at terminal velocity. We've got a very different equation that's going to make a prediction about when we're decelerating when we first pull the parachute, and a fourth different equation that's going to make a prediction about when we're floating to the ground with our parachute. So how are you going to do all that stuff at once in math? Well, there is something that allows us to do that. It's called a piecewise function. So all a piecewise function is two or more functions, which you could even call pieces, each with its own domain. Now, what's the domain again? We use that word a lot. Let's make sure we all can remind ourselves, what's that mean? The x values, good. So the domain is the set of all the input values for our function. What's the output values or the y values called? The range, okay, good. Okay, so then let's look at an example here. This is what a piecewise function looks like. So we'll look at this. Example number 1 is a piecewise function with two pieces. Okay, now let's look at each piece of this function. When you write a piecewise function, you get, there's my function notation, f of x equals, and then notice that I've got this only half of a pair of squiggly brackets, of the script brackets, only one of them. That indicates that this f of x is going to be broken up into a bunch of parts, two parts in this case. To the right of that bracket, you're gonna see 2 rows. Each row is a piece of the function, right? So we've got, for example, we could break this up into, we could call that the blue row and the red row. So I've got the blue piece and the red piece. Now, each piece is broken up into 2 parts. There's always gonna be the formula part, which is telling us what the rule is. What am I gonna do to the input value? So in the blue piece of the piecewise function, any input value I'm gonna square and then subtract 1 from it, right? In the red piece, I'm gonna multiply the input by 5 and then add 3, okay? But there's another important part to this, right? It's like there's 2 rows, but there's also always gonna be 2 columns, right? To the left, the first thing that shows up in each piece is the rule. The second thing is the domain. Think of it as where it lives, right? So the blue piece, f of x, is equal to the function x squared minus 1 only when we're inputting x values that are less than -2. If we're inputting x values that are greater than or equal to -2, it shifts gears and it becomes a different output function, right? Then it becomes a 5x plus 3, okay? So let's look at these then. What about the first one, f of -5? Is that going to be, the input value is what for part A? -5, okay. So which piece lives where x is equal to -5? The blue or the red? The blue, right? -5 is a part of the blue domain. It's a part of the x values that are less than -2. Wouldn't you agree -5 is less than -2? Right? So this is going to be a blue example. F of -5, we're going to use the blue function. That's going to equal, every place I have an x, I'm going to open up an empty quantity, so I have an x squared minus 1. What's the x value that I'm inputting? -5. So AJ, what's -5 squared? 25 minus 1 would be? Well, hold it, you told me that's 24, there you go. So f of -5, the output is -24. Okay? What about -2?
It's just 24, right?
24, you're right. 24. Thank you. Okay, what about part B? -2, is that going to be in the red or the blue domains? Red, exactly, because the red domain is all values of x greater than or equal to -2. So when x is -2, it falls in the red domain, doesn't it? Right? So I would use the red function for that. F of -2, what am I doing in the red function? I'm multiplying my input times 5 and adding 3, and my input is a -2. Okay? So Josh, what's 5 times -2? Plus 3? -7, there you go, good. So f of -2 is -7. The output there would be -7. Okay? What about +7? Bailey, +7 is going to be in my red or my blue domain. Is 7 less than -2 or greater than or equal to -2? 7?
Oh, positive 7?
Yeah.
Greater.
Greater, okay. So it's going to be in the red domain, isn't it? So then we would use the red function. F of 7 would equal 5 times 7 plus 3. What's 5 times 7? 35. Okay, plus 3? 38. Got it. Okay. So a piecewise function could have 3 or more pieces too. It doesn't just have to be 2. Like look at example 2 here. Example 2 has got 3 pieces, right? It's got a piece that exists where x is less than or equal to -4. It's got a different function that exists when x is greater than -4 and less than 1, and a third function that exists when x is greater than or equal to 1. Okay? So let's, now the next step is, let's graph one of these things, right? Evaluating them is not that big a deal. You just got to figure out my input value falls into which row, which piece of the function, and then I plug it in that row, right? What about graphing one though? Something like this. How many pieces are in this function? 2, okay. So we got, let's make them blue and red again. So there's our blue piece. Here's our red piece. So where does the blue piece live? What's going to be the boundary of the blue x values? You see what I'm saying? I mean, where does the blue region stop? It's only x values that are what? Less than -1. The red domain is x values that are greater than or equal to -1. So would you agree that -1 is kind of the transition value? That's where we shift gears between the two pieces. Okay. So let's put a vertical line there, because that's gonna separate the two regions, isn't it? Right. So there is the vertical line, x equals -1. Right. Everything to the left of that is going to be the values where we graph the blue region, right? X is less than -1. So over here, we're just going to graph, whoops, over here, to the left of my boundary, we're going to graph y equals -3x minus 7, because that's the part where x is less than -1, right? Okay, so I'm going to go ahead and just color code that whole region where we're going to graph the blue graph, the blue function. There it is. There's the blue region where the blue graph gets graphed. Okay, what about for values greater than or equal to -1? Well, that means to the right of the boundary line, doesn't it? Right? Okay, so over here, we're going to graph the line y equals -5. So this would be my red region. It's in the red domain. Okay, so I've broken this thing up into two areas. Now we got to graph each of these two pieces in their own domain, so where they live. So what about the blue graph? Let's look at that one first. So how would you graph the line y equals -3x minus 7? What would you do? So Laney, how would you graph that? If I just said graph that line, what would you do?
Go down to -7.
Okay, -7 on the y-axis. Okay. So -7 on the y-axis is, let's see, 1, 2, 3, 4, 5, 6, 7. So there's a point. And then what would you do?
I guess it's because you can't go down.
Okay.
Go up and then go down.
Good. So normally the rise over run would be go down 3 and over 1, but that's not convenient. So instead we'll go up 3 and back 1, make another point. How many points does it take to define a line? 2. I got my 2. And so then if I were just graphing this line, I would just start at that one and go through that one and just make a line that goes forever in both directions, right? So I made a light blue line, but is that the part that I'm graphing in my piecewise function? I only get to graph the part that's in the blue region, right? So I'm going to go back with a darker blue pen, and I only get to graph the part to the left of the boundary line, right? So we'll start here. And there's the part that I get to graph. Now, what kind of endpoint would I put on the blue graph? Is it going to be solid or open? It's going to be open. How come? Okay, good. Yeah, look at this. So the domain of the blue region is only the x values that are less than -1. It's not including the x value -1. So I'd have to put an open circle there, wouldn't I? Right? Okay, good. So what about the red region? How do we graph the line y equals -5? Okay, so -5 is right there. And then what's the shape of a line that's just y equals -5? Horizontal line. Okay, good. So I'm going to make a light graph there. Right? There's my line y equals -5, but I only get to graph the part that's in the red region, right? So now I'll get a darker red, and I'll go down here, starting at x equals -1, I get to start putting my pen down and graphing that piece. Is it going to have an open or a closed endpoint in the red region? Closed, good, because the red piece does include the x value -1. So that's what it looks like. There's a graph of my piecewise function. Okay? It's got different behaviors for different input values, different x values. Okay? So that worked fine. But sometimes it may not be convenient. Think how we graphed that blue line. The points that we used to graph the blue line were points that weren't actually in the blue region. That's okay. I mean, it worked, but it may not be convenient to do. What we might want to do instead, we might want to pick 2 points that are in the blue domain. So Lakaya, how could we maybe do that? Instead of picking points that are, like I picked the point, this point, and those aren't in the blue region, right? I just need 2 points. How can I get 2 points from this equation? How did you get points, like when you did a bunch of graphing in Algebra 1, how did you make points to connect to make a graph? You plugged them in, say it again? Plugged in different inputs. And then you organize those. Remember making the t-table? Yeah. Vaguely? Okay. A t-table is pretty useful. It's just a way to organize the inputs and the outputs, right? So let's make a blue t-table. So we're going to input some blue x values and calculate some blue y values. So let's pick, we only need 2. Let's pick convenient ones. Well, one of them we should probably pick is the boundary, right? So we could input an x value of -1. If I plug -1 into my blue function, what's -3 times -1? 3 minus 7? -4. So I get the point -1, -4. So I go back 1 and down 4, and there's my point. I'm going to make an open point because I'm not including that x value, right? Let's pick another one. I could pick -2, but let's make it a little further apart, how about? So if we spread the points apart a little bit, it makes it easier to graph for y. So why don't we pick something like -3? So if I plug -3 into the blue function, what's -3 times -3? Minus 7? 2. So I'd go back 3 and up 2, and I guess I didn't do this exactly right, did I? So we can go back 3 and up 2. It should have been right there. My line's not perfect. But you get the idea. Now I've got 2 points in the blue region that I can use to connect and extend and make the blue graph. Okay? Let's try another one. Okay. So, Lakai, how many pieces we got here? How many pieces in the function? How many different equations am I going to have to plug stuff into? 3. Yeah, there's 3 rows, right? Okay, so we got 3 rows. So we got, let's make them red. Oops. Red, blue, and green. So what about the red one? Where am I going to put the boundary for the red region? X equals what? 0. Okay, so we need a boundary at 0. So there's one boundary, y equals 0. Make another one. Where's the boundary between the blue and the green? 6. 1, 2, 3, 4, 5, 6. Okay, so there's my 3 regions, right? Everything, all the values of x less than 0 are going to be red. So let's go ahead and shade these regions so we can keep track of them. Everybody agree that's my red region? Okay. Everybody agree that this is my blue region? It's going to be between 0 and 6. Okay. So there's the blue region. Where's the green one go? Okay, to the right of 6, so over here. there's my green region, okay? So what's my red equation then? Y equals what? Negative 3x, good. Okay, what's my blue equation in the middle region? Okay, negative 1/2 x minus 1, good. And what's my green equation? Y equals, there we go. So all I gotta do then is just graph each of those three lines in their own regions, right? Okay, let's use our little t-table trick on this one. So for the red region, let's pick our x values. Okay, so let's see, Trent, what's one x value I definitely want to pick in the red region? Negative 3. No, you're fine. Let me ask you another question that might help out. So I'm going to graph, this is a line, isn't it? Y equals negative 3x. It's a line with a slope of negative 3 and a y-intercept of 0, right?
Yeah.
I'm going to graph that one in the red region. Well, the red region goes all the way back to negative infinity, but where does it start? Where's the edge of the red region? At 0. Okay, so that's a value we want to pick, right? Because we want to know where does this thing end when it gets to the boundary. Agreed? So we'll plug 0 in for x. If I plug 0 in for x, what's negative 3 times 0? 0. So I get the point 0, 0. So there's one point that's the edge of the red region. The edge of the red graph is going to be there, isn't it? I'm going to put an open end point because it's not including that x value. Okay? Now try to pick another one. We need one more point to be able to graph the red line. Pick an x value to plug in. Okay, like negative 3 would be one we could plug in. Okay? So if I plug in negative 3 for x, because that's a value of x that's less than 0, isn't it, right? So if I plug negative 3 in, what do I get? What's negative 3 times negative 3? 9. Okay, so I get negative 3, 9. So I go back 3 and I go up 1, 2, 3, 4, 5, 6, 7, 8. So I guess up there, right? Let's pick. How about if we pick negative 2? Or negative 1. That'd be fine too. If we do negative 2, we get what? 6. Everybody agree? Negative 3 times negative 2 gives me an output of positive 6. So I go back 2 and up 1, 2, 3, 4, 5, 6. So there's another point. 2 points is all I need. So I just connect and extend, right? Okay. All right. So Susie, what about the blue region? I'm going to make a blue t-table, and I need 2 points. Well, these ones are kind of picked for me, aren't they? Which two values, if I want to graph the line that exists in the blue region, the one with the slope of negative 1/2 and the y-intercept of negative 1, what are I really just want to pick the boundaries of that region, don't I? Right? Because I want to know what's it doing at the left boundary and what's it doing at the right boundary, and then it's just a straight line in between. Right? I mean, I wouldn't have to. I could pick different points, but wouldn't it be convenient to use 0 and 6 being as those are the edges of the blue region? So what happens if I plug 0 in? What am I going to get, Susie? What's negative 1/2 times 0? 0 minus 1? Negative 1. Good, so I get the point 0, negative 1. So 0, negative 1. Now, what kind of endpoint do I want at x equals 0? Close, good. Good, because I'm including 0. Very good. What's the other one I probably want to pick? 6. Okay, good. We'll pick 6 because there's the right edge of the blue region, right? So we pick 6. What's negative 1/2 times 6? Negative 3 minus 1. Negative 4. So we go over 6 and we go down 1, 2, 3, 4. Open or closed? Open. Good. Because we're not including 6. And then there's my 2 points. This is just a line. So we just connect and extend, right? There it is. We don't even extend. We just connect in this case, right? Okay, green region. What's the green region going to be? Mikkel, I need to pick 2 points to create my green line. And you could pick any two, but what would be probably a good choice? 6. 6 would be good, wouldn't it? Because that's right at the boundary. So if I plug in 6, what's 6 minus 7? -1. So over 6, down 1, and that's going to be open or closed? Open. The green region doesn't include 6. So we got the point right there. And then from that point, I mean, I really could even just use a slope triangle, couldn't I? The slope is 1, so I could rise 1 and run 1 if I wanted to. Or I could do the same thing by just picking the value 7. 7 minus 7 is what? 0. So I get the point 7, 0. So right there, there's my piecewise function. Okay. All right, so now, what about the domain and the range? Let's go back to our last example. Okay, we never really talked about that in the last example. This was a simpler one, right? What's the domain of this function? Now think about this. That's all the x values that I input. Okay, I guess the first thing you have to ask yourself is, are there any input values that aren't included? Are there any x values that are skipped here? If an ant were walking on this graph, is there any x value that he couldn't step on? So when he's on the blue piece of the graph, he can go all the way from negative infinity up to x equals -1. He can't, but when he gets to -1, he jumps down to the red graph, doesn't he? Right? But he still has a place to step. When he gets to -1, then he drops down to there and he steps on the red graph, and he stays on the red graph forever. So was there anything he had to jump over there? No. All x values were included as inputs. If you combine the blue and the red together, the domain was all reals, wasn't it? Right? Okay, what about the range, though? What about the range? Are there any y values that are not included? What are the y values that are included in the blue graph? There is a bottom value, isn't there? Okay, so it's everything greater than -4, isn't it? Right? The y values on the blue line are only the y values greater than -4. What about the red graph? What's the only y value that's included in the entire red graph? -5. So there's really just two parts to this. The range would be either y is greater than -4, I should say, or y is equal to -5. That's it. Okay, that's the range. And what about this graph? Let's look at this one now. If we were to look at all the vertical values combined, what are the output values that we graphed on this function? So if we start at the very bottom, there is a bottom value, isn't there? Right? All the y value, there's no y value below negative, what is that, -4. -4 is the very bottom value and it's not included, agreed? From -4, we move up along the blue graph. When the blue graph ends, it overlaps with the green graph, doesn't it? Everybody agree? So there's no y values that are skipped there. The y values, where the y value where the blue graph leaves off is where the green graph ends, and so we keep moving up. And from that point on, either green or red is going to overlap forever going upward, isn't it? Right? And so all the range, if I combine all that stuff together, and let's do that. What if I, here, I got an idea. If I do this. Okay. So let's do what we did in the past when we talked about domain and range. Let's just project the range onto the y-axis. So the bottommost value, if I project that onto the y-axis, I get an open endpoint there. For the blue region, we're just going to go up until we get to this point. What about the green graph? Well, the green graph, if I project those points over, there's an open circle there, and it goes up forever. Well, and then the red overlaps with that part, right? So the projection of all those points onto the y-axis would look like everything greater than -4, wouldn't it? Everybody agree? Okay. So we would just get the range. Y is greater than -4. Okay, what about the domain? All reals. Is it though? Hang on, let's look closely. Look at this closely. If an ant's walking along this function, he's gonna walk down the red graph. When he gets to the bottom of the red, he drops down and he can stand on the blue graph, right? He's walking along the blue graph. When he gets to the end of the blue graph, is there any place to stand? There's not. We're missing a point, aren't we? Right? There is no solid point. There's no solid ground for the ant at 6. After that, he's fine. He's on the green graph. But what's the x value that got skipped? 6, right? 6 got skipped. And so the domain here, what do you think is the easiest way to say that? There's only one value that's missing. I mean, we could say something complicated, like we could say x is less than 6 or x is greater than 6. But there's an easier way to do that. Wouldn't it be simpler just to say instead, x is not equal to 6? There's only one value it can't be. Yes, ma'am.
Okay, so you said that the X got skipped. So
Mhm.
what do you mean by that?
Okay, so look at if I were to project all this stuff onto the x-axis, right? Let's do that now. If I project all this stuff up onto the x-axis. The red graph, if I project that onto the x-axis, it's going to cover everything up to x equals 0, right? How about the blue graph? Well, the blue graph is going to fill in that endpoint and go all the way up to, but not including, 6. Now, what about the green graph? The green graph doesn't include 6, but then goes on forever. So what value got skipped? 6 did. Right? If you look at the piecewise function, 0 got included because x was greater than or equal to 0 in the blue domain, but no one grabbed 6, right? The blue domain is where x is less than 6, and the green domain is where x is greater than 6, but nobody has 6, right? There's no place where the value 6 actually exists in this function. So that's the one value that we miss, right? And so we end up, our domain is just x is not equal to 6. Okay? Does that make sense? Okay? All right. Right here, 30, 35. Okay. That's a lot. I'm going to call it quits for today. So